So in this video, we're going to discuss more examples of polytime reductions. So for this problem, called the partition problem, we're given a set S of n integers and two subsets, and the goal is to find two subsets A and B, such that A and B partition S, which just means the union of A and B is all of S, and A and B are disjoint, and we need the sum of everything in A to be equal to the sum of everything in B. So essentially, we want to split the set in half so that half the sum of stuff is on the left and half the sum of stuff on the right. But it doesn't have to be literally half. You could have one giant element in your set on one side, and then that just takes up the entire sum. But you could think of it always as like a half. So here's some examples. So you could have this set S being 1, 5, and 7, and maybe one possible partition would be to create the subset A and B, A being 1 and 5, and B just being 7. But in this example, well, 1 plus 5 is 6, that's not equal to 7, they're not equal sides, so that doesn't work. We could also try putting the green line here. Obviously that's going to fail because 5 plus 7 is 12, way bigger than 1. We could also just have 5 in its own set, so then we have 1 plus 7 is 8, and then 5 does not equal 8. And so that's all possible subsets, other than the empty in all of it, which clearly won't work. So overall, we answer no. Here, there's no way to partition the set so that the two sides of the partition are equal. Now, on the other hand, if we take this set S that has a 3 added there, now we can partition it. So what's the partition going to look like? Well, notice 5 and 3 sum to 8, and 1 and 7 sum to 8. So if we make this A and 1 and 7 B, then that gives us our partition. So we have A is 1 and 7, or 3 and 5, and then B is 1 and 7, and then clearly the sum of A equals 8, which equals the sum of B. And I'll use the notation sum of a set to mean the sum of things in the set, which is the same as that there. So in this case, we have a yes instance, and so our answer is yes. So now that we understand the problem, we want to find out an algorithm to solve the problem. And in particular, we want to solve the problem assuming we can solve the subset sum problem. So as we know, subset sum is NP-hard, so it's a very general problem, so we should be able to solve partition using it. So in particular, we want to find a polytime reduction from partition to subset sum. So recall what a reduction is telling you is we take an input to the partition problem. An input to the problem is some set S of n integers, and we need to transform that input into an input for subset sum. And recall subset sum asks you're given a set of integers S prime, and you're also given a target integer t, and your goal is to find a subset of S prime that has sum equal to exactly t. All right, so in particular, we need this transformation to satisfy S has a partition if and only if, or exactly when, S prime has a subset summing to t. So if this problem has a solution for this instance, then this one should have a solution, and vice versa, if this one has a solution, then this one should have a solution. So this gives us a valid way to solve partition using subset sum, because if there exists a partition, well, then we know there exists a subset summing to t. But if there's no partition, then there's no subset summing to t. So in both cases, we get the correct answer. So just to say that in words, if S has a partition, then S prime has a subset summing to t. And so the algorithm, the reduction algorithm, outputs true, which is correct. It outputs true because remember the output of the reduction is just the output of whatever the answer is to the subset subproblem. So in that case, we're correct. On the other hand, if S does not have a partition, then our answer should be no. Well, then by the if and only if, using the contrapositive of the converse statement, we have S prime has no subset. No subset summing to T. And so the reduction alg, outputs false, and that's correct. So that's why we prove this if and only if, because this if and only if is equivalent to showing the algorithm is correct. So the takeaway is the if and only if statement is equivalent to proving the algorithm is correct. So that's why we're always proving these kinds of statements. All right. So now how do we do this? What exactly will be our S prime and T? So we know by definition of subset sum, we can find subsets that sum to some T. And in the partition problem, we also want to find subsets of some special sum. So the key observation is that if there's a partition, then the sum of A equals the sum of B, but it partitions everything, so we also know the sum of A plus the sum of B equals the total sum of all of S, because it's a partition. And when I say partition here, I mean it's a partition of the sets, not to be confused with the partition problem. So because of these two properties, well, these both together imply the sum of A equals the sum of S over 2. And you can see that just by plugging in the sum of A here, and then you get 2 times sum of A equals sum of S. So we know we have to find a subset of S that sums to sum of S over 2. And so let's just try that. So our reduction is going to be, we'll take S and we'll transform it into the original same S, and we'll make T be the sum of S. Now, how long does it take to compute this? Well, this is going to be linear time. So it's O of n if n is the size of S. Why? Because what we have to do is copy S. That's the first part. We're outputting S, so we have to copy it. Obviously, that takes size of S equals n steps. And then we also have to compute the sum. And clearly, that's just going to take n additions. So overall, it's O of n. And so that's obviously polytime. Linear is the best we could possibly do. So it's always important to check immediately that your reduction is polytime, because if it's not, then even if it's correct, it really doesn't matter. The whole point is it's a polytime reduction. So always check that before you even try to prove your reduction's correct. Okay, so this is our reduction. It makes sense. The idea is that we know if there exists a partition, A and B, then we know the sum of A equals the sum of S over 2. And so subset sum of the instance S and sum of S will be true. Why? Because A is the subset. Where this is T. So if there exists a partition, we know subset sum will say true, so that's basically one direction of our reduction, but we also have to check both directions. So formally, we need a lemma. And this is going to be our proof of correctness, and it just says S has a partition if and only if S has a subset summing to T, where T is the sum of S over 2. So let me just move that over here. So for the first direction, we basically just proved it. So let's suppose we have a partition. So it's two sets contained in S, where A union B equals S, and A intersect B is empty. If we have this, and we know that the sum of A equals the sum of B, then by the same argument as before, we know, in fact, the sum of A is equal to the sum of S over 2, and that is exactly equal to T. And so in particular, A is a subset with sum of A equals T. So if S has a partition, either side of the partition becomes a solution to the subset sum problem for that particular S and T. And the key step here is realizing that any partition has to sum, each side sums to sum of S over 2. Now, on the other hand, let's suppose that there is a solution to the subset sum problem. So suppose there exists some A contained in S with the sum of A equals T. Well, what do we know? Well, let's define B to be S without everything in A, the set difference. And then by definition, we know that obviously A intersect B is empty. That's because we defined it to be everything except things in A, so obviously they can't overlap. And we also know A union B equals all of S, and that's again just because B is everything else. So if you take some stuff and take everything else, well, both of those combined is all of S. So in other words, it is a partition. So no, A and B are a partition of S. And then we also know, by assumption, the sum of A equals T. And so the sum of B equals the sum of S minus the sum of A. And again, this is just because it's a partition. It's the sum of all the elements not in A. And this is exactly equal to the sum of S minus the sum of S over 2, which is the sum of S over 2, and that's equal to the sum of A by assumption. So this part is by assumption. in this direction of the proof, we're assuming that property. Okay, so overall, we found a partition that satisfies the equal sum property, and so it's also correct in this direction. And so that completes the full proof. And it all fits on one screen. So we have the forward direction. If we have a partition, we can find a subset summing to t. And then we have the other direction, where if you have a subset, then you can find a partition. So really, this part is what you're usually doing in the algorithm. So instead of just asking whether there exists a partition, if I asked you to build it, this is what's actually happening. You'd be running the subset sum algorithm to find this set, and then you would use the set to build the partition by taking the set, everything else, and that gives you a partition. And in this case, just tells you the opposite's also true. If there was no partition, then there couldn't be a subset. So you won't get false positives or anything. So that's the entire proof. So that completes the reduction. So we can conclude that partition polytime reduces to subset sum. Now notice this does not imply partition is NP hard. Why? Well, remember, you want to think of the less than or equal to as saying this problem is no harder than this problem. And so what we said is partition is no harder than a hard problem. So that doesn't really tell us anything. Of course, if you reduce to a harder problem, you can use a harder problem to solve an easier one. So we've just shown that an easy problem can be solved with a hard one. That's all we've showed. So if we did want to show partition was NP hard, we'd have to switch the sides. So let's do that. Let's prove partition is NP hard. And now we're going to reduce from subset sum. So we're going to build an algorithm for the hard problem using the problem we are interested in. And so if we can solve hard problems using this problem, this must also be a hard problem. So we solve a hard problem using partition. This implies partition is also hard. And again, this is just either from transitivity or by contradiction. If in fact partition wasn't hard, well then because we have a reduction, that would imply subset sum wasn't hard, but we know it is. So now let's prove partition's NP hard. What's the reduction going to look like? So this one's a little trickier. So before it was pretty obvious because subset sum is a more general version of partition. So now this reduction's a little harder because we're using a problem that doesn't seem to capture all of subset sum. So we're going to have to tweak this S prime. So let's think about the proof and the algorithm at the same time. So let's suppose there exists some subset, I'll call it A, of S with the sum of A equals T. Let's assume we have this. So assume there exists an A like this. And now we know in the future for the proof, this needs to imply S prime has a partition. So in particular, we kind of want to use the solution A in the solution for S prime. So somehow we need A to either be or at least appear in one side of the partition. And why do we want that? Well, because if A appears in one side of the partition, we can easily extract A from that to find the solution from subset sum. Because then can easily extract it A from the partition to get the solution to subset sum. So this is usually how you want to think about reductions. If there's a solution to the problem, how can we find the solution given a solution to the other problem? So it's essentially you're thinking about one direction of the proof and then slightly tweaking it if necessary to make the other direction also work. So in particular, this is the implies direction. If there's a solution, then there's a solution. That's the one we're focusing on first. Okay, so what's one easy way for us to recover A efficiently? Well, what if there's a partition? So we want this to imply there exists a partition. A prime and B and S prime, such that A prime is just A with maybe one extra thing. That way we can easily identify that extra thing and remove it. And then B is just some other stuff we don't care about. So then if I gave you the solution to partition, you can simply get rid of the element F, and that gives you your subset sum solution. So this is what we want. So this is the idea. So what's F? What would make sense? Well, what's something really big that's easy to identify? Well, one easy thing would just be F is the sum of S. Because obviously, the sum of S can't appear in S unless there was only one element. So as long as there's more than one element, then this will be easily identifiable. This will be the only element in our new set of size sum of S. So that's nice. But if we do this, what's going to go wrong? Well, we're assuming sum of A equals T. And so if this was the case, the sum of A prime is going to equal the sum of A plus F, which equals T plus the sum of S. So for this to work, we need this quantity to become half of the total. So we want this to become the sum of S prime over 2. Now, to do that, we'll need one extra element. So in particular, notice that if T plus the sum of S is all of this, then on the other set B, what's B going to be? Well, B is just, the sum of B is going to be the sum of S minus T, because the things that sum to T, we placed in A prime. And we want this to also equal, so this plus some extra element E, we want to be equal to the sum of S prime over 2. So how do we do this? Well, if we want these two things to be equal, if we make this E here equal to 2T, then these two sums are equal. So we can just make E be 2T. And that's the idea of how you're going to derive this algorithm. So the reduction, the transformation we come up with, we design it so that the final proof will work out. And this will basically become the proof. So what's the actual reduction we're doing? we're going to make our ST transform into ST is going to become S prime, where S prime equals all of S plus an extra element, F, which we know is just sum of S, and then plus one other extra element, which is 2t, and that's our E. And so that's how we figure out what the S prime should be, by thinking about what the proof's going to look like, and also what the idea behind the algorithm would look like. We need to find a way to extract the solution from the solution for the other problem. And that kind of leads us to the correct reduction. Now, again, we have to consider the time. So what's the time here? So again, this is going to be linear time, because we copy S and then we add two elements. In particular, one is formed by sum up all of S, and the other is formed by just multiplying t. So this one's O of n, this one's O of n, this one's O of 1, and so overall it's O of n, so polytime. Now let's prove the reduction's correct. So first, let's assume S has a subset summing to t. This is basically going to be what we just said. So if there exists some subset A that sums to t, if that's the case, then what's the partition going to look like? Well, we're just going to define A prime to be A union the sum of S and then B prime, or just B, is everything else. So B is just the set S prime without A prime. So in particular, notice B, everything in B is either in S, the original S, or it's the element E. So B is contained in S union the set 2t. So each element's either in S, the original set, or it's the number 2t. And similarly, A prime is contained into the set S union the sum of S. So just as we thought before, the two new elements we constructed, one of them goes in the left side, the A prime side, and the other goes in the right side, the B side. And you can think of this as just designed to balance out what we did here. So F is designed to help you identify A, and E is designed to keep balance between the two halves. Okay, cool. So is this a partition? Well, clearly this, because of this definition, it's a partition of the set. So by definition, A prime B is going to partition S prime. But does it satisfy the sum properties? Well, we know the sum of A prime is equal to the sum of A plus the sum of S, and that's equal to, by assumption, right, the sum of A is T, and so that's T plus the sum of S. Now what's T plus the sum of S? Well, that's also equal to the sum of S minus T plus 2T, and that's equal to the sum of B. So why is that equal to the sum of B? Again, the sum of B is everything in S prime, but without the things in A prime. So what's the sum of S prime? that is that's going to be, well, the sum of s prime minus a prime is going to be this quantity. And then we also add in the 2t part because we know 2t is in there. And so the two sums are equal. And this follows just from the same reasoning we did before. So the sum of b is the sum of everything in S, except for t, because we removed the t elements that were summed by a, and then we added this extra element e. Okay, so that's one direction of the proof. That says if there exists a subset that sums to t, then we can create the partition from it. On the other hand, let's assume there exists a partition, which I'll call a prime b, actually, let me call it ab, or a prime b prime, that partitions the set S prime. And what do we know? Well, we know the sum of S is included in exactly one of them because it's a partition. So let's suppose, without loss of generality, that the sum of S is in A prime. Yeah, let me just call it B. So the sum of S is in A prime. What does that tell us? Well, by assumption, we know the sum of A prime, because it's a partition, this equals the sum of S prime over 2. And now again, what's the sum of S prime? This is just 2 times the sum of S plus 2t. Why? Well, remember, the sum of everything in S is sum of S, so that gives you one of them. And then we actually have a number that is sum of S. So both of them give you 2 sum of S. And then 2t is just a single number that we added. Remember, S prime, so let me just write out, S prime is equal to S union sum of S union 2t. So the sum of S prime equals the sum of S plus the sum of S plus 2t, which equals that, the numerator. Okay, so we know the sum of A prime is half of that, and so the sum of A prime, this is equal to sum of S plus t. And now what have we done? Well, the definition of A, because A, we're going to define A to be A prime without the element sum of S. So if we do that, well, we know the sum of A is exactly equal to the sum of A prime minus the sum of S. But remember, the sum of A prime, that's exactly sum of S plus t. And so that's exactly equal to t. So A sums to t. So that's great. We found a subset that sums to t, but A is a subset of S prime, not necessarily of S. So we need to argue that A is a subset of S. So first of all, we know there's only 2 elements we added to S prime, so we just have to show neither of them are in there. So we know by definition that the number sum of S is not in A, because we explicitly removed it from A prime. So obviously sum of S can't be in there because we literally took it out. So could 2t be in there? So also 2t cannot be in A, because then the sum of A would be at least 2t, and that's greater than t, which we know is actually equal to the sum of A. So it's basically by contradiction. If 2t was an a, then we know the sum of a is at least 2t because we get that number alone. That's obviously bigger than t itself, and that's what we know the sum of a should be by assumption. And so we know that a is actually a subset of S, and we know the sum of a is t. And that completes the proof. So if there exists a partition of S prime, then there exists a solution, A, that sums to t for the subset sum problem. And so those are the two directions of the proof. And notice how we knew what the directions would have to be, and we used them to inform how to create the reduction. And that's always what you want to do in algorithm design. Always think about what the proof is going to require while you're coming up with the algorithm so that you get both the proof and the algorithm for free. Or at least one of them's free. And this also makes sure that your algorithms are always correct because you're literally proving it simultaneously. Okay, so we know now that subset sum. So this implies subset sum. Polytime reduces to partition. And that implies that partition is NP hard. So why? Because again, we have that a hard problem is easier than partition. That's what this means. So subset sum is no harder than partition. And so a hard problem is easier than a problem implies it's also hard. And that concludes the story for partition.